Hi guys, so today we're going to discuss about why the area under the x-axis have a negative value. Okay, so why is it the case? So a lot of students, they have done integration and definite integral, and they all know that, okay, when you do definite integral, you're basically finding the area bounded by the graph, right, the function, the axis, and the limits, right? But why is it that, if that region, right, that area that you're trying to find happens to be below the x-axis, well, it'll turn out to be a negative value. Okay, so it doesn't quite make sense to have a negative area, right? Okay, so here I already brought up this example, fx equals to negative x. Okay, so we're going to find the area, right, that's bounded by fx, the x-axis, and the limits 2 to 3, right? So basically, it's the area of this, this piece that I shaded here. It's a trapezium, right? Okay, so normally, how do we do that, right? We just integrate from 3 to 2 fx dx, right? Okay, and then we're going to have integrate 3, 2, and this is a negative x. Okay, so that would give us, integrating negative x is negative x squared over 2, right? Okay, so we're going to bring in the limits now. Okay, so this is basically negative 9 over 2 minus negative 4 over 2, right? Okay, so now, okay, so what is negative 9 over 2 minus negative 4 over 2? So this is actually a plus, right? Negative 9 plus 4, right? Negative 9 plus 4 is negative 5 over 2. Oh, so our area is negative 5 over 2? No, right? So normally what we do is we can multiply by a negative, or we can do a modulus for that, right? And then, so the actual area is actually 5 over 2 units square. Okay, so that's actually the actual area, but we have to do a modulus or multiply it by a negative 1 outside. Okay, so why is it so? So why is the calculation giving us a negative 5 over 2 by default, right? Okay, so here I'm going to explain why using some limits. Okay, so I'm going to erase this part away first. Okay. Okay, so here I drew a graph, right? Y equals to fx. Okay, so okay, so let's say this point is x, right? And this is h. So this point here is x plus h, right? And this is our y equals to fx. I intentionally put a k here. This is a arbitrary limit. Okay. So what I'm going to do now is, okay, so let's say I have, I'm going to shade this. I'm going to shade this area, right? And well, I'm going to say that this area has a function, and I'm going to call this function ax, right? That means the area from this k, all the way to x, right? Okay, so now I'm going to call, okay, let's use maybe pink. Okay, so I'm going to call this area, okay, basically the area all the way until x plus h, right? Okay, so this area, okay, the pink area, I'm going to call it ax plus h, right? Okay, so what's going to happen here is I want to find, okay, so yeah, so many colors. I want to find the green area, right? Ultimately, I'm trying to find the green area, okay? So what do I do? Okay, to get the green area, okay, I have to, okay, to get the green area, I have to take the pink area minus the blue area, right? Okay, so the pink area is given by a of x plus h, and the blue area is given by ax. Okay, so we're going to keep that in mind first. Okay, now let's look at this green area only. Yeah? Okay, I'm going to form two rectangles. Okay, and we're going to talk about that. Okay, so maybe I will use a yellow, maybe. Okay, so hopefully you can see it. Okay, so I'm going to form this rectangle first. Okay. Okay, so we can see this little rectangle here, right? Okay, so how do we find the area of this little rectangle? Okay, I might as well just draw it out here. Okay, okay, so here. So we know that, this is h, right? Okay, and well, what is this? This is actually f of x, isn't it? F of x. Okay, so this is f of x. But take note that this f of x is a negative value, isn't it? Right, because the graph is below the x-axis. So naturally, it is, if you sub in this value of x into fx, it's going to give us a negative value. So f of x is a negative value. So can I say that the area of this, the area of this yellow, okay, yellow rectangle is equals to negative of h times fx. That would make sense, right? Because if fx is negative and h is positive, then your area would have been negative, right? Unless I put a negative outside here. So the magnitude of the area, right, is negative h times fx. Okay, so next I'm going to draw another rectangle. Maybe let's use a darker, yeah, let's use purple. Okay, so here we go, right? This is purple. Okay, yeah, this is maybe better. Okay, so if you look at the purple rectangle, okay, so again, I'm going to draw it here for you. Okay, purple rectangle. Okay, this is still h, right? But this length, okay, is actually f of x plus h, right? Because if you sub x equals to x plus h into fx, you get f of x plus h, which is the length of this rectangle. Okay, so the area, right? The area of this purple rectangle is, oh, so I forgot to say that f of x plus h is also negative, right? Same reason as why fx is negative. Okay, so the area of the purple rectangle will be negative h times f of x plus h, right? Okay, now let's form some inequality to help us. Okay, can I say that the green area, okay, the green area is actually bigger than this yellow rectangle, but yet it is smaller than the purple rectangle. Okay, so you can actually see from the drawing here, right? Okay, so can I say that, so the green area is given by a of x plus h minus ax, right? So, okay, I'm going to establish this relationship here. Okay, so the area is less than negative h f x plus h, which is the area of the purple rectangle. Okay, but yet it is greater than, okay, negative h f x, right, which is the yellow rectangle. Okay, now can I divide by negative h throughout? Okay, so let me divide by negative h throughout, and we will get fx. Okay, so because I'm dividing by a negative value, I have to change sign, right, of this inequality. So fx will be bigger than negative 1 over h, okay, let's call it 1 over h, ax plus h minus ax, right, bigger than f of x plus h, isn't it? Okay, so right now I'm going to take the limits, right, for this entire equality as h approach 0. Okay, so yeah, I've talked about this during my previous video, so you can actually watch it to understand what's going on if you don't. Okay, so take the limit h approach 0, fx bigger than limit h approach 0. Okay, so this is negative 1 over h. Okay, and this would be, oh, okay, maybe I'll just write it this way. I think it's easier. Okay, limit of, let's just put the negative 1 over h here, or negative over here. Yeah, okay, that'll be better. So this would be a of x plus h minus ax divided by h, right? And this is limit h approach 0 f of x plus h. Okay, now this is the good thing, right? So fx is quite independent of h, right? So, well, when h approach 0, this is still fx, isn't it? Okay, and now this is a negative. Okay, if you recall, right, if you recall, this limit of ax plus h minus ax over h, from the first principles of differentiation, right? This is actually dA dx, right? Okay, so this is a negative dA dx, all right? And okay, what about this? When h approach 0, this whole thing will approach f of x, right? Okay, so we have f of x here. Okay, so okay, if you look at this inequality, right? If you know what is squeeze rule, okay, I can say that. Okay, let's say that fx. Okay, so if this is bigger than fx but yet smaller than fx, then this is basically fx. Okay, so fx is equals to negative dA dx, right? Then can I write dA dx equals to negative of fx? Okay, and integrating both sides with respect to x. Okay, so integrate both sides with respect to x. Okay, so integrating dA dx with respect to x, you basically get a, right? And a is basically the area function, so let's just call it ax. Okay, so basically to get the area, you have to integrate fx with a negative outside. And that's the reason why earlier we need a negative, okay, to neutralize the negative value such that your area is a positive value. Okay,